Hello, my dear MIE students and friends. I hope everyone is doing well. If you hear any noise, either from my neighbor's yard or from downstairs, my older son's piano playing, I promise it's not me. So, so I'll start with the real business. It's truly my great honor to introduce today's seminar speaker, Professor Pierre Fischer. Professor Pierre Fischer is a professor at the Institute of Physical Chemistry, University of Stuttgart. He also directs a lab, internationally renowned lab, at the Max Planck Institute for Intelligent Systems. Professor Fischer received his bachelor's degree in physics from Imperial College London, PhD, I assume also from physics, from the University of Cambridge. But I promise you, he still speaks German. Good one. So he was a NATO postdoctoral fellow at Cornell University, a Rowland fellow at Harvard. He has truly international perspectives on research. You can sense where he worked. So Pierre won a Fraunhofer Attract Award and a bunch of awards I will not read to you, but important to know that he is not only a distinguished physicist, he is uniquely also a renowned roboticist. So he's on the editorial board of a science daughter journal, Science Robotics. If our students who want to publish in there do not know what they're looking for, you can consult with Professor Pierre Fischer. He knows. So lastly, his research is very broad. I'm always impressed every time I heard his talk, but all in much depth. I will not steal his thunder. We'll let him tell us some of the cool work he did. Pierre, welcome to U of T in a weird way, but floor is yours. Thank you.
Thank you, Sun. I hope you can hear me, and thank you very much indeed to you for the invitation and for the organization, also to Laura and everybody who's setting this up. It would have been nice to meet you in person all and the students, but I guess this is the way we do it now, and please feel free to ask questions, and I'm honored to be able to give this presentation here via this means. So I'm, as was mentioned, in Stuttgart, and first of all, we also have students, and this is the time when we were still allowed to be in the building without masks, and this is not so long ago, and I will be presenting work by a really fantastic group of postdocs, PhD students, and undergrads. And this is the group here that I'm very grateful for. And I'd like to tell you a little bit about some of the research we do. And I've tried to group it together and try to give it a sort of engineering perspective and an engineering question. And the question is, can we wirelessly, so without a direct physical contact, can we wirelessly move and objects and build structures? Can we fabricate things by wirelessly moving something? And I will talk about ultrasound in that connection. And the question is, can we take a sample of cells and can we somehow do something that they all fall into place into a shape that we pre-design? So not picking them up one by one, but can we in one shot make them all go into one place? So that's the first question. So we want to assemble a cellular structure. And I want to continue with a cellular structure. And I want to ask, can we actually move through a cellular structure? And here I picked, we have a lot of these companies, but here I picked a Canadian drill manufacturer. So this is the drill here. Can we drill through tissue? Of course, not with something like this, but maybe with some other kind of engineering device. And maybe we can be inspired by nature. And there are many such devices. Some of them are really nasty. This is a group at Stanford that studied this little schistosoma here that looks very weird. And that's a low Reynolds number swimmer, basically a small swimmer that swims like this. It seems pretty harmless. It's in a pond. But the nasty thing is the same creature is able to drill into skin and actually tissue and whole organs very, very efficiently. Something that the pharmaceutical industry has not succeeded in doing because most things don't make it through the skin. Yet this little nifty device does it. So how do you manipulate structures and move them through tissue? And then finally, once we've gone through tissue and we have tried to put cells together, can we actually enter a cell? That's another one of these challenges, because the cell has, of course, a membrane and a surrounding that makes it difficult to actually enter it very easily. And this we would like to do with something that we call a nano pen. And then I realized that you can already buy this. You can buy a nano pen light here. But I can tell you, we are not talking about skincare products and nothing like this, where our structures are 100,000 to 1,000,000 fold smaller than this. And I'll tell you how we try to get into a cell using light. And all of this will be wireless. So we'll try to manipulate structures in space. So that will be the theme. And I'd like to start with the first one. And the emphasis is really on, when asking these questions, can we develop new technologies, find new approaches, and maybe develop new methods that allow us to fabricate or manipulate things? And I'd like to start with this question related to ultrasound. So sound, you hear me, hopefully, is because these are pressure oscillations in the sort of 100 Hertz to 10 kilohertz regime. And in particular, for this talk today, I'll be considering more high frequency, which is then called beyond the audible region ultrasound, in particular, sort of the megahertz range. And you are probably very familiar with these sort of ideas, because bats use this as a way to locate their prey. And you may have heard the beep, beep, beep in the car when you park a car that is an echo location device, which operates at sort of 20, 40 kilohertz. So this is a way of sensing with sound. Another way that's very famous where ultrasound is used, and now we're typically in the 1 megahertz to 10 megahertz regime, is to actually take images inside the body, because the sound at this frequency is still very well propagating through tissue and not absorb too much. And by then looking at what comes back out, one can computationally reconstruct what's inside. So that's another form of sensing. But you can use sound not just for sensing, you can also do something with it, right? You can actually exert forces. So most of you probably have come across or already used an ultrasonic bath, an ultrasound cleaning device. You can actually cut cake or cheese or something like that with an ultrasonic knife. And here you don't squish the structure, but you use a sonotrode to cut it very clean. You can also weld, so you can really deliver quite a lot of power. People are thinking about interesting haptic devices where the sound will initiate a response. And you can fragment DNA with ultrasound, or even destroy whole kidney stones in medicine by the sound wave, all the way to surgery. This would be magnetic resonance guided, high intensity focused ultrasound, where tissue is being ablated with ultrasound. So you can definitely exert a force, and you can definitely do something on the actuation side with ultrasound. And the question that I want to ask is, can we use it to fabricate things? So can we take a dish with sound, with cells, apply sound, and then somehow get these structures to form, and hopefully interesting structures? And this would be a way, by having a wave, and this is an animation from a Japanese group here, where you have a speaker and maybe a reflector, and here they have standing waves. And depending on how these waves overlap, you can then use them to exert forces. Like here is a standing wave, which is used in air, where they have trapped polystyrene particles, right? And these are the sort of speakers and resonators, and then in air you can levitate these structures. These are in these sort of resonant devices, and you can see there's a force being exerted because you can hold these structures in air. And people have already also applied that to cells. You can do that and manipulate cells. Here is out of this paper. This is not our group. You can take these resonators here, you put a Petri dish, and then the standing waves will assemble the cells all in parallel. It's very benign. Ultrasound is very benign. It doesn't do any damage to the cells. And you are manipulating all of them at once, right? And but the structures you get are these very periodic structures, regular structures, because we're always talking about standing waves in a resonator design. And the acoustic radiation force acting on it will push these cells around. But if we want to do something more interesting than just lines, then we really need to be able to shape our sound field in a special way. And a resonator will no longer do, because the resonator is highly symmetric, and any interesting shape like this, we wouldn't be able to realize with a resonator. And so how can we shape sound in an interesting way? And can we then use it to push these cells maybe into a very nice structure that we design? So basically the question I want to ask, and the question that we asked ourselves, is that with light, we can project wonderful light fields and we can manipulate them. Can one think of projecting sound like that, so that we have a sound object? Well, what would be a sound object? It would be a pressure distribution defined in space, right? And since sound can manipulate particles and cells, well, if we had these particles and cells in solution, would they then assemble right away in one shot into the shape that we want to here defined with a sound field? And this would be really wonderful, because then you could manipulate and focus ultrasound beams, which you can then use, for instance, in medical applications. You can define your beams, you can steer them around, or you can make these organoid-like structures. So it would be really good, and you can then hopefully get some interesting structures and shapes, and are not restricted to having them in a very regular array just by looking at the interference patterns of standing waves. And so how do you get interesting fields in general? Well, you can use more than one source. So you might have more than one transducer, and if you change the relative phases, they will interfere. And if you have a fair number of these sources, they could all interfere, and you can, for instance, design a focus. And that is the joint interference of them. But let's say you want to do something more exotic, like this dove here. What is if you want to define the pressure into this image, not just a focus? Well, this is a complicated target image, and so you need many, many transducers. And this is really very, very difficult, because you would have to transmit power, you have to electronically drive them, you have to make sure they're all phase locked, etc., etc. And this is here a slide from a group, Bruce Drinkwater's group in Bristol, and they have taken some of these distance measurement ultrasound probes that you have in the car, 64 of them, and aligned them like this. And with this, and look at all the cabling and the spaghetti you need to control this, they are able to define a trap for a particle here. So it's still some ways away for defining this, say, P stuff, right? And the difficulty is the scaling. It isn't possible to extend this very much. Even if we get inspired by looking at what do medical ultrasound scanners do, well, they have a few hundred elements, at most maybe 1,000, and that's about it. And they also detect the sound, so they are detecting usually weak signals. We want to project strong signals, where you then might have mechanical coupling effects and other things. So it's much, much harder. And imagine you had to design and draw a picture with 1,000 pixels. Well, that typically doesn't get you very good images. So how to go about it? And we were wondering about this, and try to take some inspiration from what happens in optics, right? And in optics, we can, for instance, form very interesting fields. And the inspiration here is from Denis Gabor, who got the Nobel Prize in Physics for inventing holography. He actually invented it to try and improve electron microscopy. That was his motivation. And what we see on the right-hand side here wasn't possible, because the laser came much, much later after this invention. So can we use a similar idea? And this is the PhD project of Kai Melde. And the idea is very simple. Let's just use one transducer, not hundreds of thousands, just one. But on top of that, let's place a hologram. So, and the hologram here is now, you can see it there, is a material that has different thicknesses in various points. And if you imagine like we are now, for instance, in water or so, then you would take a sound wave that would be propagating through this material. And let's say this is a polymer. And depending on the thickness, you have some sound waves that are going all the way through water, and others are going through the polymer. And because the sound speeds are different between water and the polymer, there is a relative phase difference that that develops from one point to the next, that is a function of the thickness of this profile. So you now have a way of essentially defining lots and lots of little point emitters that are that have a phase that's given by the thickness of this plate. And so Kai wanted to test this idea and indeed generate a sound wave pattern that is here Picasso's P stuff. So the idea is that we have a simple single transducer plane wave source that will then go through our hologram plate, whose thickness we need to design in such a way that all the phases of this wavefront diffracts, that at a certain distance we get the image, the target image that we want. And you can do this computationally by using algorithms which are, for instance, used in optics, like the Gershberg-Saxton algorithm, where you iteratively, and we are using a form which is called the iterative angular spectrum algorithm, which is better suited for this purpose, where you have here everything has the same phase as the wave enters, you propagate it, and then you fix a boundary condition, namely whether the amplitude is where you want it or not. And then you change these amplitudes, propagate back again, and keep the phases, and you update this until you iteratively arrive at your target image. And then running this computation, you get a phase front, i.e. this would be the cross section of the sound phase front, that must have this sort of phase distribution so that the sound wave will diffract and give you this image. And now you need to, and you see that it's from -pi to pi here, now you need to translate that into a thickness profile. And this you can then do by using something like 3D printing, and you just make this plastic plate here, which has a thickness profile where each thickness corresponds to this phase. And even without trying very hard, for ultrasound at 2 megahertz, a 3D printer can already give you, in essence, 15,000 sound sources or pixels. And so one could imagine that this then allows you to generate this image. And this is the experiment. This is the hydrophone scan in water, in ultrasound, region of 2 megahertz in a solution. So you have a transducer above it, you have this hologram, and you are in a solution, and you measure and you scan, and we get this pressure distribution, and the high pressure are the lines of this P stuff. So this is a sound image. I think it's the most complex ultrasound image that has ever been formed. And you can really now start playing with this, because you can design these sound fields. And remember, sound fields should exert forces, right? And we're very pleased to say that this is already being used also for other applications. This is a Spanish group. They are using this hologram to compensate for changes in the thickness, which every human skull has. So it's at some places a little thicker and some is a little thinner. If you take an X-ray image and you make this sort of hologram, you can compensate for this thickness profile to get better ultrasound foci if you're using this in medicine. So let's check whether we can manipulate matter like this. And here we are in liquid here, everything is water. There is the transducer, there is the hologram above. We have a little chamber that is just defined by some thin polyester sheets, and inside there are particles. And now we look from above, and the sound is switched on, and these PDMS particles then assemble in the image, the target image. So we can manipulate matter like this, and they are being pushed because they show a density difference, and they have a different sound speed to their environment. So there is a force exerted on these particles. If the sound is off, it will all fall apart again. Now, I started and motivated this by trying to put cells together. So let's put cells in a suitable medium and try and exert a force, and then see if we can form an object like this. And this is work by Zhishao Ma, and he was actually surprised. These are cells, human colon cancer cells, that form this focal point here. And we were amazed that it works so well, because the cell is mainly water. So the acoustic contrast isn't very, very high compared to, let's say, some inorganic particles. And what turns out is that the ultrasound also gets absorbed by the fluid, and it pushes a fluid flow, which moves the cell to the region where we want it, and then the sort of trapping takes over and localizes the cells. And here are two more images. There's a line being formed, and here we have a Pac-Man. and these are just cells in a growth medium, which you can then take out and put it in the incubator. We weren't allowed to publish the Pac-Man because the Pac-Man, it turns out, is still under copyright. And so I hope nobody sues me now as we are showing this Pac-Man image here. But we can manipulate the cells, and just in case the first image causes legal problems, here is the Minerva of the Max Planck Society, and these are again cells being formed. But this is great, and we'd like to do one better because we'd like to do this dynamically, right? If we have one fixed hologram and we get one fixed image, that's nice, and we're very pleased with it, and we can do many things. But the question is, can we maybe also change this pattern, and can we basically project a movie like you do with light? Can we project ultrasound movies? And for this, we would need some kind of way of manipulating the ultrasound dynamically. And again, we can take inspiration from light, and you may be familiar with a spatial light modulator. This is a device like this, which has millions of pixels, and you can change each little pixel. You can change the optical properties in such a way that you can define the phase of the light going through it. And it's a liquid crystal device, like your monitors that you're familiar with. And each little cell element, you can apply a voltage, and you can then switch between a nematic aligned phase and an isotropic disordered phase. And this little change, whether the molecules are aligned or not aligned, is good enough so that the light will experience a different refractive index and a different phase propagating through each of these pixel elements. So you can define the phase at each point, which means if you define all the phases, you can form interesting images, as we know you can do with light. And the thing is, if you put in some typical numbers, the refractive index difference here is roughly 0.1. The wavelength, let's say, is visible light 500 nanometers. Then you can work out, you just need a liquid crystal cells of some 5 to 10 microns, and you can really get any phase you like. Is that possible with sound? Well, let's do the Gedanken experiment and ask whether if we use a polymer and water, and actually the sound speed does not differ very much for many materials. If we wanted to do the same thing, and we wanted now between one element and another pixel element to have the same phase difference we can very easily do with light, well, it turns out we would have to make one element here in this particular case for these numbers 4 millimeters bigger. But there are no actuators in the 100 micron regime that can get you such a difference in length. You can also not get such differences in material properties, expansion or whatever it is, to such a degree. Maybe you can change things by a few percent, 10%, but not like that. So that's the challenge. It's not easy to find something that can be used to manipulate ultrasound. But let's not just give up, because there's also another way with which you can manipulate sound. And that's, for instance, used in many light projectors, which are based on these MEMS devices, right? So you have these MEMS mirrors, and these MEMS mirrors, they can switch and tilt. And depending on whether they tilt in the direction you want or not, you can project light. So it's like an on-off switch. Now, is there maybe an on-off switch for ultrasound? And again, that's not so easy, because we can't just reflect ultrasound like that. It would just go straight through. And anyway, these devices operate in vacuum. So how to unblock or block sound very easily? And there is a simple way, and that's a bubble. Even a 10, 20 micron thick air bubble is good enough to really not let any ultrasound through. In fact, the transmission coefficient can be as low as 10 parts in a million, 10 to the minus 5 here. So it really is a very good sound blocker. Now, what we would need to do is we need to sort of have bubbles appear and disappear, and then we could project sound images. So how to do that? So the idea is we need to make a device, and the device needs to generate bubbles so it can block sound. And where it doesn't generate a bubble, the sound will go through, and then we can generate something which would be an amplitude hologram, right? So where we have bubbles or not, this would be the amplitude hologram. And then in the image plane, we could be able to generate what we want to do. And then we could update this, and we would have a dynamic device. And so we collaborated with colleagues at the University of Stuttgart, and this is a chip, it's a CMOS chip that has 10,000 gold electrodes here. This is the wiring for it, centimeter device. And the idea is now that we are actually going to put the ultrasound underneath the chip. We send the ultrasound through the chip, and at the top end of the chip, we have these gold electrodes, and there we can then perform electrolysis and generate a gas bubble, and that we can then do by control. So here's the device. The transducer is underneath. It actually goes through the CMOS chip that sits on top, and then we end up in our chamber where we then generate our ultrasound patterns. And here is the animation. This is the chip where we're writing bubbles now with a CMOS chip, 10,000 gold electrodes, and we're writing these little microbubbles. And the microbubbles, they are then used to either let light sound through where there aren't any, or block it. And this is now a movie that Zhishao Ma took with ultrasound. In fact, it's the ultrasound pattern here. This is the target image, and this is what happens in solution if you scan it very, very carefully. So we have a sound projector there, and we can use ultrasound to assemble materials by design, which is new, and it's a one-shot method, and it isn't serial. And we can use it also to assemble cells. And what we're working on, because the field, of course, is propagating through space, is to make that work in 3D, which is done here in this particular wavefront of the ultrasound wave. We've encoded 3 images as it's propagating. So we are hoping, and we are working very hard to try and define an arbitrary shape in space and define with it the sort of object we would like. Then we have the right kind of material in there, for instance, cells, and we hope that they will form in one shot. And so then we have a cellular structure. So that was my first little story. I'll now come to another story in the theme of wireless manipulation, and that is, can we then, if we have a structure, it might be very exciting to penetrate or move through it without having to be connected to the outside world. So this is the penetration. Why would you want to do this? We are collaborating with medics at the University Eye Clinic Hospital. And for instance, they need to inject through the eye, and then they inflate behind the retina to deliver genetic material, because intravitreal delivery is difficult, because the sort of body of the eye has a very complicated molecular structure which hinders the transport. And so we're wondering, could we engineer a little micro or nano device that we can use to transport through this medium to reach the cellular levels back here? And the question is, how mesh-like is this sort of vitreous, this eye body? And we can do this by using paramagnetic particles like Chen Q has done, and then we can pull them through, and we can measure which ones make it and which ones get stuck. And we find that if you look at the size, there is no motion. As they get smaller and smaller, they still get stuck with 1 micron, but at 500 nanometers and below, it starts to kick in and it starts to move. So we need to really engineer things now on the sub-micron level if we want to find some nice agents that are small enough to slip through the vitreous and make it through the vitreous body of the eye. And for this, we're using some fabrication techniques. There are gas phase fabrication techniques that are based on old ideas, but we've recently pushed this to the nanoscale. Here is the basic idea. You're familiar with this. You can heat a material, and if you heat a material, you can it forms a gas plume, and it can then condense on a substrate and form a thin film. So we're doing this at a very strong angle, at a called oblique angle, glancing angle. And I'll say a little bit about these particles in a minute, but imagine you have some particles, and now a simple shadowing rule will mean you can deposit wherever there's a particle, and that means that's where the material will grow. And then if you manipulate your substrate during the growth, you can then start forming interesting objects. And this we want to do to build sub-micron structures. And here is a little animation how this would work. So we're using E-beam deposition. This would be the substrate, and then there would be a deposition of material there, and we can choose the kinds of materials. We can do one after another, or we can then even combine with ALD and make core shell, or we make alloy structures on whole wafers very quickly. And we can sonicate this off and transfer it to solution, and then study them in solution. And one of the things we've now been doing for quite some time is to make these small structures that have a drill-like shape. They are roughly the size of a bacterial cell. They can be smaller. And in this particular case, you are looking at a wafer here, and about 1 billion of these structures per square centimeter. And we can include a little magnetic moment, and then we can steer them with fields and move them around like is shown in this animation here. This is a real speed animation of one of these structures going through solution, and we can steer them very nicely. And so the idea is maybe we can use them as our untethered agents to move through the vitreous. And we can make them from the bacteria size all the way down here. This structure has a thickness of 70 nanometers only and something like 300 nanometer length. So it's actually smaller than any swimming organism. And then we can transfer them to solution and steer them and move them. And let's try and see if we can reach here the back of the eye to deliver material. But there is another challenge, because if we just take one of these structures and put it into the vitreous, this is deep inside the vitreous, it's actually not going to move, because engineering and building and is difficult, because you have to really pay attention to the chemistry and the physics and the material properties. And in this particular case, it just gets stuck. And that is because, again, this is a interesting biological structure made out of hyaluronic acid and collagen fibers, and they have regions which are positively charged, negatively charged, hydrophobic, hydrophilic. So it's really difficult to find something that doesn't get stuck. If it's small enough, it might go through, but it sort of has an adhesion problem. But then Zhiguan Wu was inspired by these plants here, the Carnivorous pitcher plant, which has this amazing coating so that nothing really is able to withstand it, and these ants, they fall inside. And he borrowed this idea. That's also known as slips, which people have developed here in this publication, which are essentially fluorinated compounds, and we are using a perfluorocarbon silane with which these structures are coated. And then on top of that, and that's not an easy task, they are coated in a little perfluorocarbon liquid layer. So there's a liquid layer around these structures. And you can check that all the molecules are there and that it has the right sort of properties. And then we can revisit our experiment, and where without a chemical coating, they got stuck, because they were small enough to make it through potentially, but because of adhesion, so they were able to slip through in principle. But here we show, once you put the coating on it, they are able to maneuver themselves through this network because they are smaller than the network, and they have the correct coating not to get stuck. And this is something that Zhiguan Wu and Tian Qiu have shown here by injecting into an eye, and they propagate about 1 centimeter to the retina. They have very good direction. And here is an OCT image where you see there is a swarm, probably 10,000 of them, that are reaching the region of the retina. So here is a way to make a wireless transporter. But one of the things that are always immediately come to mind is, what about the magnetic material? I mean, that clearly is a difficulty when it comes to biological systems. And but there's good news. There are these totally biocompatible and non-cytotoxic supermagnets. They are as strong, really almost, as the best and strongest magnets, the little magnets that you can buy and you might have in the lab, these neodymium iron boron magnets, which are super strong. And this is really very fascinating material science, because you add platinum, which otherwise is not magnetic, to iron, and you make this iron platinum, and if you bring it in the right phase, it's the L10 phase, I'm sorry, it's a little cut off here, then you can get very strong magnetic properties. This is work by Vincent Kadiri in collaboration here with these collaborators, which we've published this year. And if you look at the magnetic properties, this red line here, if we look at the magnetization as a function of the applied field, that would be iron. The green line would be nickel, which is typically a strong magnet. And here you have a very nice magnetic properties here for a hard magnet, which is the black line, which is the iron platinum. So here is good news, very strong magnetic moments, and we can anneal these structures and build them into our little micro and nano devices. And this is what Vincent did, and he was able to actually take he used a coating that meant that the cells took up these propellers, and he could deliver and stain the cell, and the cell is alive, and we were able to transfect it. And that then brings me to the last story. So we've made cellular assemblies with ultrasound. We've considered another wireless way of moving through them with a magnetic drill, and we reached the cell. And what I've just showed you here was basically uptake by the cell itself. It wasn't actively getting into the cell. So can one enter the cell in a controlled way? Can we drill into the cell? And this is now the last story, and these are going to be our optical nanobots or nanopens. And that we can motivate by asking, how does one normally get things to enter a cell? Now, either you rely on the natural uptake of a cell that will gobble up things, including nanoparticles, or you try and help it, which there have been a number of techniques developed. Magnetofection is that you have magnetic particles and you pull them close to the cell. You're not actually pulling them into the cell, you're just increasing the contact time between the particle and the cell, which increases the chance for uptake. Or you use ultrasound again, sonoporation. You very briefly cause the membrane to rupture, and that could then let things in. And the same with an electric field, which is called electroporation. But the difficulty is that this is not controlled, right? That will open up anywhere some openings and make the membrane permeable. And what I'd like to ask here, and this is the project that was done together with Theo Lohmüller and Jochen Feldman at the LMU, I want to ask the question, can we take a particle and we can decide where it enters the cell, and can we bring it in? And we're not going to do any of these existing methods. We're going to do something which probably sounds quite crazy, because we want to deliver organic molecules at the end of the day. We're going to take a particle and we're going to heat it to more than 200 degrees centigrade, and then we push it into the cell. Let me tell you how we want to do this. And for this, I'd like to tell you about the optical tweezer, which many will know about. Arthur Ashkin won the Nobel Prize in 2018 for it. It's a very useful tool in biophysics. And what it relies on is, imagine this is a laser beam here, which has an intensity distribution. So it's very intense in the middle and less intense on the sides. And let's imagine this is a particle, like a microparticle, polystyrene particle or whatever. And what now happens is that if we have photons coming close to the center onto the particle, they get refracted, i.e. they get sent to the left, but you need to conserve momentum, which means there must be a force which pushes the particle to the right. Now, it will also have some photons on its left side entering, but they are less intense, right? It's a sort of laser beam which has a lot of intensity in the middle. So here are less photons going to the right, so the force to the left is weaker, which means overall there's a force to the right, and the particle wants to go to the center, to the location of highest intensity. And if you have a focus, you can thereby trap or tweeze the particle, hence the tweezer. And you can do fun things with it. This is from a group in Amsterdam, and they are playing Tetris with particles inside a liquid by rustering a laser into the fluid and holding it long enough where there is a particle, right? And so they are moved around solution entirely by this tweezing force. And this is, of course, a really wonderful application. If you then switch off the laser, all the particles will wander off and be gone. Can we use this idea for our purposes? And the idea is that we need to bring an agent close to the cell, and then we need to somehow exert a force to get it in there. And this is it. And we're going to use the same fabrication method that I've talked about before to make this what we call the nanopen. So it has at one end a gold cap, a gold particle of something like 80 nanometers. And then on top of it is a rod-like structure, which is made from an oxide, in this particular case, aluminum oxide. And the whole thing is submicron, it's about 500 nanometers in length. And the idea is we can use the oxide structure to couple molecules to it. So we can couple molecules to it, and then we can get them into the cell, and we can use the tweezer to locate it and send them in. So how are we going to send them in? Well, first of all, we need to position it. And for this, you essentially move laterally the laser beam, as in an optical tweezer, to position it. And then by changing the intensity of this infrared trapping beam, you can cause different effects. There is one force that wants to bring it to the center, but there's also a scattering force and a thermal force acting on the particle, which means that changing the intensity, you can sort of change like an elevator its height. Moving the beam around laterally, you can position it. And doing this with this beam causes really no heating. So it's really still room temperature, so there's nothing happening here. But now once we're at the right position and we've coated this with our fluorescent molecules, we can add another beam, and that's what Theo Lohmüller actually has done. He's added another beam, a green beam, and switches it on for a short period of time. And the green beam is resonant with the plasmonic structure, and it causes heating. And it will heat briefly to a very high temperature, something like 500 degrees centigrade here, certainly well above 200 degrees centigrade. And that causes a very small bubble which bursts and which will rupture the membrane. That's how it works. And so here are some images. These are the impact sites that you can see in the image. These are little ones because there has been little laser power used for heating. And here are bigger ones if you use higher laser powers for heating and opening the cell membrane. And these are the molecules that he was able to bring in. So they're very happy they survived, because that's an important thing. Even though we're heating the tip to several hundred degrees, the body here stays cool. So the nanopen body stays cool enough, actually at room temperature. So all of these organic molecules beautifully survive, as we can see here, because we can detect fluorescence, and Theo Lohmüller can detect fluorescence and locate them inside the cells. So we have a light-driven controlled injection pen to get organic matter and into cells. And with this, I think I'm at my 40 minutes or so for this little overview of some of the work that we've done recently. And the theme here of the talk was wireless micromanipulation and nanorobotics. So first is, can we do things with sound that wasn't possible until very recently, namely shaping it in a very high and sophisticated controlled way with high resolution, so that we can form interesting objects, maybe cellular structures. And we are working towards one-shot fabrication. Can we wirelessly move through complicated structures like organoids or tissue? And there we looked at magnetic nanopropellers. And finally, how can we position something on a cell and enter a cell to deliver material to a cell with a light nanopen? And so this is really what I wanted to tell you today. And the big thank goes to the people who did all the work, the funding agencies, and you for your attention. Thank you very much.
Thanks so much, Pierre, for the wonderful talk. Is Laura still online? Do you want to read questions to Professor Fischer?
Yes, sure. Are there any questions from the student side? I don't seem to have received any. Oh, one just came in right now. So from Cameron, how do you build the ultrasound hologram plates?
Yeah, thanks. They are essentially is a map of height, of thickness, right? And then the 3D printer does layer by layer and adds material by just going layer by layer and printing a correct thickness. So it's a normal 3D printer, and all that you present it with is essentially a little disk, and you make this disk sometimes a little higher and sometimes a little thinner. So you make, if you like, a topographic surface with a normal standard 3D printer. And all you need to do is you need to know what is the sound speed in your polymeric material, and then you know, aha, if this is the sound speed, and if I'm in, say, water, that is the phase that will be accumulated. So we use a very simple standard 3D printer, and all we tell it is make a plate that has different thicknesses at each pixel location.
Excellent. Okay. From Armin now, how did you coat the micro swimmers with liquid without causing stiction?
Yeah, that's an excellent question. And that was the wizardry of Zhiguan Wu. And yes, you're absolutely right. And if you imagine that your coating is something like a fluorosilane or fluorinated compound that also doesn't like water, then if they come together, they would immediately agglomerate, right? And so the way he did it is actually by, because we fabricate them on a substrate, on a wafer, he coated it while they were apart, while they were spatially apart, and then dried it. And then after drying, he immersed them by sonication into solution. So they then were not close enough. And then when they were basically, again, fluid-like structures, they could then not agglomerate anymore. So it is actually a multi-step procedure. He's laid it out in the paper. It involves chemical coupling, it involves drying, it involves suspension, and it was and then in a fluid medium where they then don't agglomerate. So it's a tricky procedure, but it actually works very well.
Excellent. We have someone who raised their hand, so I'm just going to allow them to speak.
Hello, Dr. Fischer. This is Xinyu Liu. Thanks for
Hi.
the great talk and fascinating results. And we learn a lot for those all kind of activation mechanisms. I have a quick question about this first ultrasound hologram. Have you any ongoing work to push the technology for three-dimensional micro object manipulation instead of having assembly, like moving things around out of the plane? I think that would be very cool because we have seen some of those large-scale acoustic manipulators. One of the videos you also showed. So any ongoing work on that direction?
Yeah, so indeed, I mean, I think there are two aspects to your question, which is very good. I think one is like the 3D aspect, and this is, and the other one is manipulation. And the answer is yes to both. So 3D is very exciting, but it's a difficult problem. It's actually a difficult problem because it's an inverse problem. You are trying to define an object in space, and you somehow must figure out how to get to a planar representation that has the correct phases so that these all come together and form this 3D thing. And if you imagine you have a volume where you define an object, I don't know, maybe my teacup here, that's the object I want, then each voxel has to have a certain amplitude, and I don't want to have any amplitude around it, so I define this. And now you have to project out, and each point projects to each point on the planar representation. Each of this can have a phase. You immediately end up with astronomical possibilities on how to combine all this. So this is actually a computationally very demanding problem we're working on, trying to figure this out. And that is one. It kind of works already for some simpler structures. And so, yes, we're working on 3D, and we hope to have results there soon. And by using this dynamic spatial ultrasound modulator, the SUM that Zhishuo Ma made using the CMOS chip, we can then dynamically, and we have done this, we can manipulate particles, and we have done this in small scale. So we can dynamically update this. But what we haven't yet put together, because the 3D is still work in progress, is to do 3D micro manipulation. And this is still on the to-do list.
Cool. Thanks a lot.
Thank you.
Excellent. We have another person who raised their hand. I will allow them to speak.
Hi, Professor Fischer. This is Bing Bing from Professor Xinyu Liu's lab, who just raised the question. And my question is from non-expert sides, because for the magnetic robotics, could you tell us a little bit more about the difference between your group's research and others like Joseph Wang and the Meeting Cities? Because for me, those kind of shape of magnetic robots seems quite similar for me.
Yeah, there are lots of groups. There is also actually in Toronto, Yusun is an expert on it. And then there is Bradley Nelson at ETH Zurich, who is one of the pioneers. And there are a lot of groups working on small scale manipulation. So the first thing that you need to pay some attention to is the actual length scale. Okay, so micro is something that many people refer to as being very small, but for some of them it means 1 micrometer, and for other people it means they have a hard time seeing it on their table. And so there is actually also already a difference in spectrum of structures that are being made, because some are really very, very, very small and others are just small. And then Joe Wang's group and others, including ours and many groups, Ayushman Sen, Tom Maluk, and many groups, Sanchez's group, and they use chemical reactions to propel particles and then add in addition a magnetic field to steer them. Now there you have a propulsion because the particle is moving by a curious mechanism that is called self-phoresis. So it itself is chemically being propelled by the fact that it's generating product molecules. Then there are groups like Bradley Nelson's group, and we were more or less at the same time, I think in the same year, publishing these small structures. They are working on slightly larger structures. They've also pioneered the use of 2-photon writing to make these structures. With 2-photon, you can only get a size down to 150 nanometer a voxel. So the structures end up being bigger, which is useful in many cases. The fabrication method that we use is able to produce very, very small structures. As I said, I mean, we can make this down to 90 nanometers. So they have different uses. If you make your structure smaller and smaller, you can carry less, so that might not be advantageous. Here we focus on penetration of tissue, where there seems to be in many regions a real benefit on being on the submicron scale. Others are working in bigger fluid volumes, and there it then makes sense to have bigger structures. Others are manipulating inside cells, and so there is a whole spectrum, and I think it depends on the application, and it also depends on the mechanism. And I think unique to these sort of corkscrew methods, that was Brad Nelson's group and my group that were some of the first to really do this corkscrew propulsion at this length scale.
Okay, thank you. Thank you for your brief summary.
Okay, we have another question here asking for the ultrasonic fabrication, what would have to be changed for it to work in an air medium?
Yeah, so you basically have a different wavelengths there, right? And so it becomes a little harder because the sound speed is very different. So to make very, very small structures, this is very good in water. And of course, you can also use the buoyancy of objects. But there is absolutely, this is a totally general principle. So you can apply it to any frequency range and any wavelength. So you can also do this then if you wanted to with ultrasound in air. There are some issues that if the frequency is too high, it gets difficult to actually propagate the sound. So the principle is very general, and you can also use it, and for instance, use it in the hundreds of kilohertz or 40 kilohertz range, and then you can also apply the same principle in ultrasound, only your wavelength is a lot longer, and so the structures that you can potentially be forming are much bigger then, not so small as here.
Okay, another question. In our lab, we use magnetic fields to move particles. Usually, I see labs making complex magnetic fields by increasing the number of EM coils. Do you know if you can make magnetic holograms with a single coil and some sort of hologram plate, maybe made of soft magnetic material?
A magnetic hologram. Yeah, so that is a little tricky because the hologram is relying on a propagating wave, right? So you have a propagating wave that is expanding in space and it has an amplitude. And this wave, and in the case of the pressure wave, it's a longitudinal wave. If you are talking about electromagnetic waves, then they are propagating, and then you end up with things like light or radio waves. Now, with light or radio waves, you can use holograms and you can form interference patterns. But if you are using coils in your setup, then most likely you are using quasi-static or static fields, and they are not propagating, and then you cannot form these interference patterns very easily. What you can do, nevertheless, is you can have different regions and you can shape your magnetic field, but it wouldn't be quite the same thing, because this is an effect that is known as diffraction, and it relies on a propagating wave, which wouldn't happen for a static wave.
Okay, from another student, do you think the third approach, the optical control, can be done in vivo one day?
Yeah, that's probably unrealistic, right? I mean, this is not going to be very easy. Although people have and are working on the idea of heating plasmonic particles with infrared light. Light doesn't enter the body very well. You may know that there is a sort of transparency window, which people call around 100 nanometers to 1 micron, which they like for medical applications, because you can get a little bit deeper into the body. But you don't really get very far. So you might get in a centimeter or so. It's still useful. People are using this, for instance, in optoacoustic methods to do imaging and things like this in a small mouse. But deep inside the human body is really tricky because the light doesn't get in. But nevertheless, people are using plasmonic particles, for instance, in conjunction with treatments of skin-related cancers and subcutaneous type medical problems where you could be destroying tissue with plasmonic particles. But I don't believe that this will be a way to treat heart cells or something like this.
Okay, from Neda, what happens to the robot after they're done with their mission? Can you take them out or degrade them somehow at the site?
Yeah, that's a question that is that comes up, and it's a very good one because it's clearly a question: what happens if you leave material behind, and what happens if you leave very small material behind, nanomaterial, micro, and a lot of things isn't known because the properties or the behavior is different depending on size. And well, in principle, there are two things. One is, in principle, you could basically rotate them the other way, and then like a corkscrew, it should be propagating backwards. Now, that is often not so practical, but in principle, and here there could be the advantage of having a larger object. If you have a larger object, then it's very feasible. You could go in, and once you're in, you just drill the other way and you come out again. And that is indeed a very plausible way. Now, at this size, it's probably less realistic, and they may also then just get stuck somewhere. And there, the option is to use biocompatible and non-cytotoxic materials in addition of things that might actually cause these to dissolve. And that is not so uncommon because people are using, for instance, implants that are there that after some time dissolve. So that would be a strategy, but it is a question that would have to be addressed.
And on the topic of materials, someone also asked, what is the material used for the ultrasound hologram?
Yeah, this is something very clear. It's just a printing material that you commercially buy that comes with a 3D printer. It's nothing special. Most of these ultrasound is or sound in general is really difficult to work with, in the sense that it's easy to work with experimentally, but it's difficult to work with because it is almost the same everywhere. So with light, you get things like different refractive indices, you get different, you can do lots of things with it. And in sound, is almost everything is the same. It shows no non-linearity. Most materials are just purely linear, and it has very little dispersion, i.e. the sound speed is always the same. So we just use a commercial printing material. Sound speed in the plastic like that is something like 2,400 meters per second. And any other nice clean material could be used, and it's not limited to a particular material or a particular printer.
Excellent. To generate the ultrasound for 3D rapid assembly, is there a specific type of transducer that is preferred?
No, we just work with a higher power because we need to illuminate a higher region. The regions we work with is bigger, so we have volumes of sort of 2, 4, 5 centimeter on the side length of a cube, and we want to project enough. But it's a very simple planar transducer, nothing special. In fact, they're also very cheap, actually. So nothing special at all. We like to work with megahertz ultrasound because you get high resolution. And if you get into much higher, something like 10, 15 megahertz, which would also be the upper limit roughly sort of for medical imaging, then the absorption of the sound in water becomes more dramatic. So low megahertz we like to work with, and the transducers are just straightforward commercial transducers for this frequency range.
And another question here, what's the effect of the nanopen on cell viability? It seems that it is intrusive.
Yeah, it is intrusive because you're basically causing a little explosion to the membrane, right? You are forming a gas bubble, and the bubble cavitates, and that causes a rupturing of the cell membrane, and that opens it up for a short while. And the viability, the exact number I would have to look up, but something like 75% of the cells were still happy afterwards, as shown by the right kind of fluorescent dyes that make sure the cell is still operating, and 25% did not make it. And it's the same is actually true with many of these other methods, some of which are also medically used. People are using sonoporation to very briefly open the blood-brain barrier, and that's essentially also it's essentially a cavitation which causes a destruction, and this destruction or shock wave, this will rupture membranes and cause things to become more permeable. So they are all the same. We are doing, like, if you like, a little nano explosion, and 75% of cells were happy with that. And when I say we, that was Theo Lohmüller who did this.
Excellent. We can move more so into the student Q&A period now. We have one more question here, but I encourage all the students, you may ask questions that are not necessarily even related to this specific presentation if you have any general questions that you'd like to ask Professor Fischer. But someone asked if you would ever do work on in vivo treatments.
Yeah, I mean, yes. I mean, if things are at a stage that they can actually do something, and I think that's the question one has to ask: is there a real medical benefit? And we believe in special, in very clear, well-defined cases that is the case. And we are working together, including with a startup company that is pursuing this sort of thing. But it needs to be very well defined, and we think there are some cases where some of the technological applications really have hopefully a benefit and will prove to be something useful that will transition out into the clinic in the long run.
Wonderful, Pierre. Maybe before students pose non-research related questions, we had about 120 people in the audience. We still have 90 left, because some students take courses after 10 minutes after each hour. So I looked at your dynamic hologram, the bubbles. See if I can make a limited number of electrodes to increase the number of pixels. So what is my limit in terms of imposed by the wavelength of the sound wave?
Yeah, so I mean, it's absolutely correct that at some point it makes no sense because the ultrasound has a certain wavelength. If you are in the low megahertz, it will be hundreds of microns, 500 microns. If you go up, it'll become less. And so then it really makes very little sense to have even finer structures. So this is actually a very nice length scale because it fits very nicely with which can be done conveniently with photolithography and other techniques, right? And so it then makes sense to go to this sort of wavelength limit of what the sound wave is at this particular range and have as many pixels as possible, but it doesn't make any sense to go beyond that. And that is typically on the sort of few hundred micron size scale. That's the wavelength.
That makes sense. So I guess students start to ask you, so for my students in here, MIE students, Professor Fischer has a lot of experience, editorial boards, working at different institutions, please don't be shy to ask any questions about your research, about career development, or anything at all. We have it for another 15 minutes. So
and I stop sharing now, is that right? Does that make sense? And it's no longer being recorded, is that right? Or
yes, correct. I will.
And I should stop sharing, or?
Yes, you may go ahead and do that.
Okay,
Thank you.
Good.